Hello everyone, my name is Abhishek. I'm a PhD student from Purdue University. I'm very excited to be presenting our research work and would love to hear some feedback on that. I also want to thank IEEE Censors for this wonderful opportunity. The topic of the presentation is amplitude recovery of saturated sinusoidal signals. The other contributors to the project are Mohit Singh and Byunghoo Jung. The agenda will be as follows. In the introduction, I'll talk about the motivation and give an example of where this technique can be used. Then I'll talk in detail about the working principle. Then I'll present the simulation results and discuss an important issue to take care of while using this technique. That will be followed by the conclusion. The introduction. This technique is applicable to sensing systems that rely on measuring the amplitude of a sinusoidal signal for measuring the physical parameter of interest. This can be seen in systems such as electromagnetic-based tracking systems, where depending on the amplitude of the received sinusoid at the receiver coil, the distance of the transmitter coil is found. The voltage that is induced on the receiver coil is then amplified by the analog front end and then sampled using an ADC. Now, if the transmitter gets too close to the receiver, the signal may get saturated if the amplifier gain in the analog front end is fixed. In such cases, the dynamic range and the accuracy need to be traded off. To counter that, variable gain amplifiers are typically used to dynamically vary the gain to maintain an appropriate amplitude within the ADC range. This has a couple of issues, however. Firstly, this increases the circuit complexity due to the feedback, and then it also increases the area of power consumption and cost. Automatic gain control loops are used to control the gain. This results in finite settling time, which might become an issue for systems that require fast response time or low latency. Also, gain inaccuracies due to variation in feedback and input resistors with process and temperature may pose issues. To mitigate that effect, high resistance values are typically used, but that adds to thermal noise. Thus, there is a need for recovering the amplitude of saturated sinusoidal signals to increase the dynamic range without compromising on the accuracy, while avoiding the need for VGAs when possible. That is, to use traditional analog front ends. Now to talk about the working principle, consider the case of symmetric signal clipping, where the signal gets clipped within plus or minus V linear. Each sample can then be classified as either linear if it is within plus minus V linear or saturated otherwise. In one cycle, there are 4 such regions that are linear. The number of linear samples and the total number of samples in each cycle are then counted. Having done that, this equation can be written where Tsat is the time instant at which the signal starts getting clipped and T is the time period of the sinusoid. Now, this ratio of Tsat over T can then be used in the equation that describes the expected unsaturated sinusoid to obtain the estimated value of the amplitude, which is A. In the most general case, with the presence of a known DC value, the clipping becomes asymmetrical. The time instances where the signal starts to get saturated, T1 and T2, corresponds to VL1 and VL2, which are the saturation voltages. They are related by these set of mathematical equations. They can then be written into an overdetermined system of equations in this matrix form. Then, using this technique of least squares estimation, the formula for the estimated amplitude can be found. But note that here we still need to find the ratio of T1 over T and T2 over T. This can be obtained as follows. Proceeding as before, samples can be classified into top saturated if they're greater than VL1 and bottom saturated if they're less than VL2. Now within each cycle, it can be seen that T1 can be related to the number of top saturated points using this equation, which then simplifies to give a formula for the ratio of T1 over T. Similarly, using bottom saturated points, a ratio for T2 over T can be obtained. Having obtained these two estimates, they can be used in the final equation for estimating the amplitude of the sinusoid. Moving on to the simulation results, a 32 kHz sinusoidal signal was used with a sampling rate of 1 megasamples per second, and then sampling jitter and Gaussian noise were also added. A linear voltage range of plus or minus 1.65 volts was used to clip the signal. Finally, a 50 cycle window was used for recovering the signal amplitude. It can be seen that the recovered amplitude closely follows the expected amplitude for the small signal amplitudes, and the performance is not affected by DC. However, the performance gradually worsens with the increasing amplitude. This can be better seen in this plot of error versus the expected amplitude. The error increases because the fraction of saturated samples to the total samples in each cycle approaches 1. It was found that for an average error of less than 10%, the signal recovery up to 20 times the saturation voltage was obtained, with a sampling rate of 1 megasamples per second. And expectedly so, the net error decreases with increasing the sampling frequency. However, it was found that the error increases dramatically whenever the sampling frequency is a multiple of the signal frequency. This can be understood as follows. When the sampling frequency is a multiple of the signal frequency, the number of samples and the number of saturated samples in each cycle is fixed. So, the error that results in a single cycle remains fixed over multiple cycles. So, the sort of averaging does not really improve the error. On the other hand, when the sampling frequency is not a multiple of the signal frequency, the number of samples and the number of saturated samples in each cycle does not remain fixed. So say for in cycle I, the ratio of Tsat over T may be less than the ideal. In another cycle, it might be greater than the ideal ratio. So over K cycle, the error averages out to give a good estimate of the amplitude as the average starts tending towards the ideal value. In conclusion, we have developed a novel method for recovering the amplitude of saturated sinusoidal signals. This helps in improving the dynamic range of sensing systems that use a fixed gain amplifier in the analog front end. This technique is applicable for single tone sinusoidal signals with the frequency and the DC level known. The biggest advantage is that the algorithm is simple enough to be implemented on low-end microcontrollers with a small code footprint. The software implementation allows for easily changing the algorithm parameters as per the application. Simulations show less than 10% absolute error up to 20 times the saturation voltage for a sampling rate of 1 megasamples per second. The performance improves when the sampling rate is increased. Also, this technique is not restricted to sinusoidal signals alone. It can be extended to most periodic signals by following a similar methodology. Thank you so much for listening to the presentation. I would be happy to answer any questions that you may have to the best of my abilities.